welcome to this session. So, we are looking into the solution of elliptical partial differential equations, which will be representing the steady state of a process of any process. So, let us look into a two-dimensional problem, elliptical partial differential equation, and we will be looking into the ill-posed problem, because in an actual problem it will be an ill-posed problem, because all the boundary conditions may not be homogeneous at proper places, proper boundaries. So, therefore, we have already seen how to break down the problem depending on the number of non-homogeneities present into the system, how to break down the problem into sub-problems considering one non-homogeneity at a time, and thereby forcing a converting an ill-posed problem into an well-posed problem. So, therefore, now we will be looking into the well-posed problem. If we know the solution of the well-posed problem, we can always convert an ill-posed problem into well-posed problem and go ahead with the solution. So, the first problem we will be dealing with is del square u del x square plus del square u del y square is equal to 0. So, it is basically Laplacian. Laplacian equation is given by this del square u in two-dimensional. The grad square operator or the Laplacian operator is represented as del square del x square plus del square del y square. So, let us fix up the boundary conditions. At x is equal to 0, you have u is equal to u naught. At x is equal to 1, we have u is equal to 0, and y equal to 0 and 1, we have u equal to 0. Let us consider a Dirichlet boundary condition at x is equal to 0, that is u is equal to u naught, that is specified in all the three boundaries. That means, at x is equal to 1 and y is equal to 0 and 1, we have the homogeneous boundary conditions. So, if you look into this system, we will be having a standard eigenvalue problem in the y direction only, not in x direction, because the boundary conditions in the y direction are homogeneous. So, we will be having a standard eigenvalue problem in y direction only, as BC's are homogeneous there. So, again it is a linear operator. So, we go ahead with the separation of variable type of solution. Consider u is a product of sole function of x and sole function of y. So, we are then going to substitute this into the governing equation. So, if we do that, we will be getting y d square x dx square plus x d square y dy square is equal to 0. We multiply we divide both sides by x y. So, we will be getting 1 over x d square x dx square plus 1 over y d square y dy square is equal to 0. So, we will be formulating a standard eigenvalue problem in the y direction, because the boundary conditions are homogeneous in that direction. So, we write 1 over y d square y dy square is equal to minus 1 over x d square x dx square. The left hand side is a function of y, the right hand side is a function of x alone. They are equal, they will be equal to some constant, and this constant has to be a negative constant in order to have a non-trivial solution in the y direction. So, we formulate the eigenvalue problem in the y direction, d square y dy square 1 over y is equal to minus lambda square or d square y dy square plus lambda square y is equal to 0. So, this is the eigenvalue problem that we formulate in the y direction, and the boundary conditions are also satisfied by the original boundary condition in the y direction, that at y is equal to 0 and y is equal to 1, capital Y is equal to 0. and we have already seen the solution of this. The eigenvalues are n pi, where the index n runs from 1 to infinity, and eigenfunctions are the sign functions is y n is equal to C 1 sin n pi y. So, these will be giving the solution of y varying part. Now, let us look how the solution of x varying part will be obtained. So, if you look into the x varying part, that is very important, 1 minus 1 over x d square x d x square is equal to minus lambda n square. So, this that is lambda n, since lambda n is n pi. So, it will be n square pi square. So, write a subscript n to denote the solution corresponding to nth eigenvalue. So, d square x n d x square is equal to n square pi square x n. So, if we take it to the other side, d square x n d x square should be minus n square pi square x n will be equal to 0. So, we know the solution of this. The solution will be consisting of e to the power n pi x and e to the power minus n pi x. So, if we do that, so x n will be nothing but C 1 exponential lambda n x plus C 2 exponential minus lambda n x, where lambda n is nothing but n pi. Okay. So, this is the solution of x varying part. Now, let us look into the governing equation, the boundary condition. The boundary condition of the x varying part must satisfy the boundary condition of the original problem. That means, at x is equal to 1, we had the homogeneous boundary condition, that is x is equal to 1, we had capital X n is equal to 0. So, if we put that boundary condition, let us see what we get. 0 is equal to C 1 exponential lambda n plus C 2 exponential minus lambda n. Therefore, we can get C 2 is equal to minus C 1 exponential 2 lambda n. So, once we do that, then we can write down the governing equation of x n. So, C 1 exponential lambda n x, C 2 is minus C 1 exponential 2 lambda n exponential minus lambda n x. Okay. So, we take C 1 common. So, that will give you exponential lambda n x minus exponential 2 lambda n exponential minus lambda n x, and then we take exponential lambda n x exponential lambda n common outside. So, it becomes exponential minus lambda n exponential lambda n x minus exponential lambda n exponential minus lambda n x bracket n. Then we take minus common. So, it will be C 1 exponential lambda n. This becomes, this will be in the front. So, it will be e to the power lambda n 1 minus x minus e to the power minus lambda n 1 minus x. Then we multiply and divide by 2, if we do that, this becomes sine hyperbolic function. So, it minus C 1 by 2 will be a new constant, let us say C 1 prime exponential lambda n, and this become this will be this will be multiplied by 2 and divided by 2. So, minus 2 C 1 will be C 1 prime. C 1 prime will be a new constant, that will be minus 2 C 1. So, C 1 prime exponential lambda n, and this will become sine hyperbolic lambda n 1 minus x. So, that constitutes the solution of x n. So, we will be able to write down the complete solution. U n is nothing but x n y n. So, u n y this is C 1 prime exponential lambda n sine hyperbolic lambda n 1 minus x times sine n pi y, and u will be as a function of x and y will be summation of all this solution by putting them up by using the principle of linear superposition. So, we construct the complete solution by summation of u n, where the index n runs from 1 to infinity, and this will be okay, C 1 prime multiplied by C 1, it will be a new constant maybe. So, it will be new constant C n prime. So, summation of C n prime n is equal to 1 to infinity exponential lambda n sine hyperbolic lambda n 1 minus x sine n pi y, where lambda n is nothing but n pi. Okay. Now, we have the complete solution in front of us, except the evaluation of the constant C n prime, and C n prime now will be evaluated from the from the unused boundary non-homogeneous boundary condition, that is at x is equal to 0, u is equal to u naught. So, we utilize the condition at x is equal to 0, u is equal to u naught. If we put that boundary condition, we will be getting u is equal to u naught summation n is equal to 1 to infinity C n prime exponential lambda n sine hyperbolic lambda n 1 minus 0, that is x equal to 0 sine n pi y. Okay. So, it becomes u naught is equal to n is equal to 1 to infinity C n prime e to the power lambda n sine hyperbolic lambda n sine n pi y. Now, this C n prime now evaluated by utilizing the orthogonal property of the eigenfunctions, that is the sine n pi y sine function. So, I multiply both sides by sine m pi y dy and integrate over the domain of y from 0 to 1. See what we get, 0 to 1 sine n pi y dy, and this will be sine m pi y dy, and this will be n equal to 1 to infinity C n prime e to the power lambda n sine hyperbolic lambda n, and this will be sine n pi y sine m pi y dy from 0 to 1, and using the orthogonal property, once you open up the summation series, all the terms will vanish except one term where m is equal to n, and that term we will be having on the right hand side. The summation sign by opening up the summation, we will be having one term in the right hand side that will survive, it will be integral sine square n pi y dy. Okay. Then changing the running index from m to n, we will be having u 0 0 to 1 sine n pi y dy, will be Cn prime e to the power lambda n sin hyperbolic lambda n 0 to 1 sin square n pi y dy, and we know that these will be returning a value of half. So, it becomes u 0 1 minus cosine n pi over n pi Cn prime by 2 e to the power lambda n sin hyperbolic lambda n, and we will be able to get the solution of Cn prime as 2 u 0 e to the power lambda n sin hyperbolic lambda n 1 minus cosine n pi divided by n pi. Now, we will be substituting Cn prime into the complete solution and see what we get. So, if you look into that, the complete solution is now, if you look into the solution as in terms of Cn prime, it was n is equal to 1 to infinity Cn prime exponential lambda n sin hyperbolic lambda n 1 minus x sin n pi y. So, therefore, now I am going to substitute Cn prime expression of Cn prime. So, this will be n is equal to 1 to infinity Cn prime is 2 u 0 exponential lambda n sin hyperbolic lambda n 1 minus cosine n pi over n pi sin hyperbolic lambda n 1 minus x sin n pi y multiplied by exponential lambda n. So, there was an exponential lambda n here. So, you can write exponential lambda n there. So, this exponential lambda n and exponential lambda n will be cancelled out, and you will be getting the complete solution as n is equal to 1 to infinity 2 u 0 1 minus cosine n pi over n pi sin hyperbolic lambda n is n pi. So, it will be n pi 1 minus x divided by sin hyperbolic lambda n, that is n pi sin n pi y. So, that gives the complete solution of an elliptical partial differential equation in 2 dimension, where the boundary condition at x is equal to 0 is u naught, and all the 3 boundary conditions are homogeneous and Dirichlet. So, you will be getting the complete solution like this. So, in the next example, I will be considering the boundary condition instead of boundary condition at x is equal to 1 x equal to 0, I will be considering the boundary condition at x is equal to 1 is non-zero, all the other boundary conditions are homogeneous and 0. So, let us look into that. So, we will be solving the partial differential equation del square u del x square plus del square u del y square is equal to 0, and at x is equal to 0 we have u is equal to 0, at x is equal to 1 we have u is equal to u naught, and at x is equal to at y is equal to 0 and 1 we have u is equal to 0. So, now in this particular problem, the boundary condition located at x equal to 1 will be assuming a non-zero boundary condition, non-homogeneous boundary condition, but everywhere else it is a Dirichlet boundary condition. Let us say how the solution looks like. We will be getting a separation of, we will be attempting a separation of variable type of solution. After separating the variables, we will be having 1 over x d square x dx square plus 1 over y d square y dy square is equal to 0. We will be formulating a standard eigenvalue problem in the y direction, because the boundary conditions are homogeneous there. So, therefore, 1 over y d square y dy square will be is equal to minus 1 over x d square x dx square is equal to minus lambda square, in order to have a non-trivial solution. So, if we now formulate the governing equation of y, will be nothing but lambda square y is equal to 0 at y is equal to 0 and y is equal to 1, your capital Y is equal to 0, in order to confirm the boundary condition of the original problem in the y direction. We know the solution of this problem, the eigenvalues are n pi and eigenfunctions are sin n pi y. So, we have the eigenvalues as n pi, lambda n is equal to n pi, and eigenfunctions as y n is equal to C 1 sin n pi y. Now, let us look into the x varying part. So, if you look into the x varying part, we are going to get is d square x dx square minus lambda square x is equal to 0. So, you can put n corresponding to nth eigenvalue. So, x n will be C 1 exponential lambda n x plus C 2 exponential minus lambda n x. Now, the x varying part we had the in the boundary condition in the original problem, at x is equal to 0, capital X must be equal to 0. In the original problem we had at x is equal to 0, u is equal to 0. So, that part at that boundary capital X must satisfy that. That means, at x is equal to 0, capital X has to be equal to 0. So, if we do that, we get 0 is equal to C 1 exponential lambda n into 0 plus C 2 exponential minus lambda n into 0. So, it will be 1. So, we will be getting 0 is equal to C 1 plus C 2. From there, we will be getting C 2 is equal to minus C 1. If we do that, then we will be getting x n is equal to C 1 exponential lambda n x minus C 1 exponential minus lambda n x. So, we will be having C 1 exponential lambda n x minus exponential minus lambda n x. We multiply and divide by 2. So, 2 C 1 will be having, this will be a sine hyperbolic function, sine hyperbolic lambda n x. So, this will be new constant, let us say C 1 prime sine hyperbolic lambda n x. Now, we will be able to write down the complete solution. So, u will be u as a function of x and y will be nothing but summation of x n y n, where index n runs from 1 to infinity, and this will be C 1 prime and C 2, it will be a new constant C n prime or maybe C n sine hyperbolic lambda n x cosine sine lambda n y. Lambda n is basically n pi. Now, we will be utilizing the boundary condition at of the original problem at x is equal to 1, u is equal to u naught, and then to evaluate the undetermined constant, the leftover coefficient C n, and it will be u naught is equal to summation C n sine hyperbolic lambda n sine lambda n y. Then we will be evaluating Cn by utilizing the orthogonal property of sine function. So, if you do that, you will be getting u0 integral 0 to 1 sine n pi y dy is equal to summation n is equal to 1 to infinity Cn sine hyperbolic lambda n integral 0 to 1 sine n pi y dy, and if you open up the summation series, all the terms except one term, all the other terms will vanish, only one term will survive when lambda m is equal to lambda n. So, it will be sin m, we multiply both sides by sin m pi y, and all the terms will vanish except m is equal to n, and then we change the running coefficient m into n. So, we will be getting 0 to 1 sin n pi y dy is equal to Cn sin hyperbolic lambda n integral sin square n pi y dy 0 to 1, and we know this will be nothing but half, and this will be 1 minus cosine n pi over n pi. So, I will be in a position to evaluate Cn now. I will be writing directly the expression of Cn 2 u0 1 minus cosine n pi over n pi divided by sin hyperbolic lambda n or n pi. So, that will be giving the complete solution of Cn. Now, we will be able to write down the entire solution in terms of u and x y. U x y will be nothing but summation of Cn. So, this will be 2 u naught 1 minus cosine n pi over n pi sin hyperbolic lambda n x divided by sin hyperbolic lambda n sin lambda n y. So, lambda n is basically n pi. So, it will be 2 u naught n is equal to 1 to infinity 1 minus cosine n pi divided by n pi sin hyperbolic n pi x divided by sin hyperbolic n pi sin n pi y. That will be giving you the complete solution. Similarly, we may have a non-homogeneity appearing in the x direction, in the y direction, and boundary conditions in the x direction may be homogeneous for a well posed elliptical partial differential equation. That means, we may have a problem something like this: del square u del x square plus del square u del y square equal to 0. At x is equal to 0 and 1, u is equal to 0. At y is equal to 0, you have u is equal to 0. At y is equal to 1, you have u is equal to u naught. In this case, we will be formulating a standard eigenvalue problem in the x direction, because the boundary conditions are homogeneous in the x direction, and in the y direction we will be having the hyperbolic functions. So, the solution of this equation will be exactly similar to this, only the thing is that the eigenvalue problem will be defined in the x direction, and 2 u naught, it will be 2 u naught n is equal to 1 to infinity 1 minus cosine n pi divided by n pi sin hyperbolic n pi y divided by sin hyperbolic n pi, and this will be sin n pi x, because we will be having a standard eigenvalue problem in the x direction. Similarly, we can have the non-homogeneity at y is equal to 0 and homogeneity at y is equal to 1, and x in the x direction both the boundaries are homogeneous. So, in that case we will be having a standard eigenvalue problem in the x direction, and in the other side, in the y direction we will be having the other problem. So, it will be the first elliptical problem we have solved, but in this case the eigenvalue problem will be in the x direction instead of y direction. So, that is how the well posed problems in elliptical well posed elliptical partial differential equation can be solved. So, I will stop here in this class. In the next class, what we will be doing? We will be looking into a an actual 3-dimensional or 3-dimensional problem, which will be having more than one non-homogeneity, and I will break down the problem into other sub problems, and will be then convert the ill posed problems into the well posed problem, and we know the solution of the well posed problem. So, after that we will be looking into the solution of hyperbolic partial differential equation, well posed hyperbolic partial differential equation. Then we will move ahead with the cylindrical coordinate system and spherical polar coordinate system, which will be quite often in any process engineering system. Thank you very much.